This is Lesson 18 in our Calculus 2 series, Volumes by Slicing, including discs and washers. We're going to start this lesson on volumes by talking about how we can find the volume of this loaf of bread. We're going to make slices of uniform thickness delta x and approximate the volume of each slice. Now, how can we approximate the volume of a slice? We can find the area of the face of the slice and multiply that area by delta x. So the volume of the ith slice will be the area of the face of the ith slice, which we call A of xi, multiplied by delta x. And so that's an approximation to the total volume that we're looking for the loaf of bread. Now, the more slices we take, the better the approximation, so we let n go to infinity. And in the limit, we have the definite integral. So the total volume is the integral from a to b of a of x dx, where a of x represents the area of the face of the slice at any x value. We can also say that's the area of the cross-section at any x value. Now, we don't have numbers here to go with this loaf of bread, so we're going to now talk about a more mathematical example. Find the volume of the described solid S. The base of S is a circular disk with radius r. Parallel cross-sections perpendicular to the base are squares. Okay, it says the base of S is a circular disk with radius r. So here is our circular disk at the base, and we have radius r. And it says that parallel cross-sections, meaning parallel to each other, perpendicular to the base, so they're made perpendicular to the base, are squares. So these cross-sections are all squares. So now I've set this circular disk up along the x-axis, so we have some frame of reference. And so the volume of this solid is going to be given by the integral from a to b of a of x dx. Remember that a of x is the area of the cross-section that's perpendicular to the x-axis. So in this case, that's the area of the square cross-section here. Right? So at any x value, we want to know what's the area of that square. That's what we want to integrate here. And then dx represents the thickness of the slice, right? That used to be delta x, and then when we take the limit as n goes to infinity, that becomes dx. And then a and b are the bounds on x, so in our case, our bounds are going to be negative r to r. So what we need to figure out is now a of x. Based on any x value at which we're taking a slice, what's the area of that square? Well, to determine that, we need to find the corresponding y value for the point on the circle, because this y value is half the side of the square. So x is the distance along the x-axis, and then y is going to be given by radical r squared minus x squared, because this is the circular disk of radius r. So the equation for that circle is x squared plus y squared equals r squared. That means for any x value, the corresponding y is going to be what we get when we solve for y here. And I'm choosing the positive side just to make it easier. That's radical r squared minus x squared. So that says that a side of our square here is twice that distance. And then our area function for the area of the square is going to be side squared. So it's going to be 2 radical r squared minus x squared all squared. So that's 4 times r squared minus x squared, and that's our a of x. That's the function that we need to integrate. So we integrate that from negative r to r. Remember that we're integrating with respect to x, so x is the variable and r is some constant. So integrating here, we have r squared x. And integrating here, we have x to the third over 3. And we still have our 4 on the outside. So we're here And then we just integrated on x. We plug the r and the negative r in for x when we evaluate our integral. And so that gives us 16r to the third over 3. So I know these kinds of problems can be intimidating when you first look at them, but really they all work the same. These are volumes by slicing, and we're always going to be integrating the area of a slice. So we set it up along an axis so that we can integrate along that axis. So we integrate with respect to x here, and we're slicing cross-sections perpendicular to that axis. And then we can find the area of the cross-section. And it's always going to work this way. So let's take a look at another example. The base of S is the triangular region with vertices 0, 0, 3, 0, and 0, 2. And cross-sections perpendicular to the y-axis are semicircles. Find the volume of S. So now we have cross-sections that are perpendicular to the y-axis, so that tells us that we are going to be integrating on y and looking for a function a of y to be the area of those cross-sections. And notice the cross-sections are semicircles. So you need the area of the semicircle, but you need it in terms of the y at which you're making the cross-section. So first set up your base, then sketch in your cross-sections and see how you could represent that area as a function of y. And set up your integral and find the volume. Please pause the video and work on that. So here are the vertices of our triangle, and so this represents the base of our solid. So I drew it here in a little bit of perspective so that we can put the third dimension in and have the semicircle cross sections. But just looking at the base, that's described here. Now the cross sections are taken at each of the y values, and so we need the area of the semicircle in terms of the y value at which we're slicing. Well, we know how to take the area of a circle using radius. The area of the full circle would be pi r squared. So the area of the semicircle is going to be 1/2 pi r squared. But the thing is, we have to figure out how to represent this radius in terms of the y at which we're slicing. Well, let's take a closer look at the base here. We realize that the radius of the semicircle is 1/2 of the x value. That corresponds with that y value. Okay, well, what's the relationship between x and y? We can find the equation of this line, and that gives us the relationship between x and y. We have the point 0, 2 here and 3, 0. So our slope is -2/3, our y-intercept is 2, and so here's the equation of that line. Y equals -2/3 x plus 2. So for any given y value, we can solve for x in terms of y. X is equal to -3/2 times y minus 2. Notice that the radius that we need for our semicircle is 1/2 of x. So r is -3/4 of y minus 2. So our area of the semicircle, 1/2 pi r of y squared, looks like this. And so we simplify a little bit, we get 9/32 pi times y minus 2 quantity squared. And we're integrating over the y values from 0 to 2. And so we're here, we get 3 pi over 4 as the volume of our solid. So again, the first thing we did here was sketch the base. They gave us the vertices of the triangular region, and they said the cross sections perpendicular to the y-axis were all semicircles. So that gives us the solid with this framework. Now we know that we're always going to be integrating the area function. It's the area of the cross-sectional slice. And we know that area here is a semicircle. So we know that we're going to have a of y being 1/2 pi r squared, where r is also a function of y. So we need to represent this r as a function of the y value at which we're slicing. So we recognize that 2 times r is equal to x. We found the relationship between x and y, and that allowed us to solve for r in terms of y. And so then we integrate our area function, and we got 3 pi over 4. Now let's take a look at volumes by slicing when we have solids of revolution. So consider the region bounded by y equals radical x and the x-axis over the interval x going from 0 to 4. That's this region. And now let's rotate this region around the x-axis. We're going to have a solid that looks like this. And here's a computer-generated version of the outer surface of the solid. Now, how can we find the volume of this solid? We find the volume by considering slices of the solid, and the slices are formed by making a cut in the region that is perpendicular to the axis of revolution, and following that through the revolution. So here's the axis of revolution, that's the x-axis. So we make a cut in the region perpendicular to the x-axis. So we've got this red cut here, and then we're following that through the entire revolution. And notice that's giving us a disk, a circular slice in that solid. So we have a cross section that is a circle, and so how can we find the volume of the solid? We want to integrate the area of this circle. The area at any x value here is going to be pi times r of x squared, where r is the radius of the circle, and it of course depends on the x value. And in this case, that distance, that radius, is radical x. It's given by the function. And so our area function is pi r squared. So pi times radical x, quantity squared, or just pi times x. Remember that because it's a solid of revolution, any slice is going to be a circle, and so we're always going to be using pi r squared for our area. And it's just a matter of getting the right r of x formula, or we'll see later could be r of y, but it's a matter of getting the right formula for radius for our integral. And in this case, the radius of that circular disk is radical x. It's given by the function height here. And so we're just integrating pi x as x goes from 0 to 4. And so we get 8 pi as the volume of our solid. Now I want you to take a look at the region bounded by y equals radical x equals 0, and y equals 2. I want you to find the volume of the solid generated by revolving the region around the y-axis. Now we're going to be revolving around the y-axis, so the cut that you make, the slice that you make, is going to be perpendicular to that, and it's going to be an integral on y. So take a couple minutes, sketch the graph, see if you can sketch the solid of revolution, find your radius, and integrate. Please pause the video and work on that. So we're given y equals radical x, y equals 2, and x equals 0. So the purple region here is the region that we revolve, and we're revolving around the y-axis now, so our solid of revolution looks like this. And when we're computing volumes by slicing, we slice perpendicular to the axis of revolution. So that gives us this disk here. That's a representative disk that we have. Now notice the radius here is the x value. Well, that's great, but we want to integrate along y. So we need to represent that x value in terms of y. Well, this is the function y equals radical x, so x is then equal to y squared. So r of y is equal to y squared in this case. And so the area function that we have is pi times r of y squared. And so we're here. Simplifying and integrating, we get 32/5 pi. Let's take a look at another. we want to consider the region bounded by y equals x squared and y equals radical x. Now notice they're not giving us any x bounds here, so we need to make a proper sketch including the points of intersection. And so that's here, that's this purple region. We have y equals x squared on the bottom, y equals radical x on the top. And we're going to revolve this around the x-axis, and we want to find the volume of the solid generated by revolving the region around the x-axis. So we revolve this around the x-axis. And now how can we get the volume of only this region revolved? Well, very similar to what we did in the last lesson with computing the area between curves. Here we want a subtraction of volumes. We have a larger volume that's given by the outer curve, y equals radical x, and then we have a smaller volume that's given by the inner curve, y equals x squared. And so we want to take the larger volume minus the smaller volume. So we're going to subtract these two integrals, and we can write that in terms of one integral, but please note that this is capital R of x quantity squared minus little r of x quantity squared. You have to square before you subtract because it comes from two separate volume integrals. Each one is a pi r squared. And I can't tell you how many times I see students do capital R minus little r and then square, and that's wrong, so don't do that. Now our capital R represents the larger radius, so we're taking the distance from the axis of revolution to the outside radius, and so that's a distance of radical x in this case. And the smaller distance is from the axis of revolution, the x-axis, to the bottom curve, which is y equals x squared. So that's just x squared for little r of x. And our x values are going from 0 to 1. So our integral looks like this. So we simplify and integrate, and we get 3 pi over 10. And this is called the method of washers. So I don't know if you're familiar with your hardware, but this is a washer. And so we're going to consider the outer radius as capital R, the inner radius as little r, and then its height here for us is going to be delta x or delta y. But let's talk about the volume of this washer. We're taking the volume of the bigger cylinder and subtracting from it the volume of the smaller cylinder. So we have pi capital R squared times h. So that's the area of the circle multiplied by the height, so that's the volume of the bigger cylinder. Subtract from that pi little r squared h, that's the volume of the little cylinder. So we have pi times capital R squared minus little r squared, all multiplied by h. And so this is what we're seeing in our integral. Pi times capital R squared minus little r squared, and then the h is the delta x, is the thickness of the washer. Because what we have here is a washer with thickness delta x in approximation, and in the integral that delta x becomes a dx. So our method of washers looks like this. And certainly we could have this in the y direction as well, so we would have pi times the integral from c to d, capital R of y squared minus little r of y squared dy. So now I want you to take a look at the example where we have the region bounded by y equals sine x and the x-axis over the interval from 0 to pi. And we want to find the volume of the solid generated by revolving that region around y equals -1. So first I want you to sketch the region, sketch the axis of revolution, figure out your capital R and your little r, and integrate to find the volume. Please pause the video and work on that. So here we have y equals sine x going from 0 to pi, that's the shaded region. Here's y equals -1, our axis of revolution. And then I tried to sketch this region as it would look revolved around the line y equals -1. And so it should look like a bead. It has a cylindrical hole through the solid. And so remember that capital R is the distance from the axis of revolution out to the outer curve. So now how are we going to measure capital R here? The top value for capital R is y equals sine x. The bottom value for capital R is y equals -1. So we always measure our vertical distances as top minus bottom. So that's going to be sine x minus a -1. So that's sine x plus 1. And then little r is going to be the distance from the axis of revolution to the inside curve. Well, we might be able to just see that that's 1 unit, so little r of x is equal to 1, but formally that's y equals 0 minus y equals -1. That's 0 minus a -1. So now we have our capital R and our little r, and so we want to set up the washer method for volume. Our x values are 0 to pi, so those are the bounds on our integral, and so we're here. So in the interest of time, I'm going to leave out the steps of the solution here, but this integral turns out to be pi times pi plus 8 over 2. We would want to square out and simplify, and then you'd have a sine square x that would have to get replaced by a 1/2 1 minus cosine 2x, and continue from there. Let's take a look at one more problem. Find the volume of the solid generated by revolving the region around x equals 2. The region is bounded by y equals x and y equals radical x. So first thing you're going to do is sketch the region, sketch the axis of revolution, find your outer radius, find your inner radius, set up your integral, and solve. Please pause the video and work on that. So here's our shaded region from y equals x to y equals radical x, going from 0 to 1, the points of intersection, and we're revolving this region around x equals 2. And so here's the washer that we get. Now remember that we're slicing perpendicular to the axis of revolution, which means that we're going to have a horizontal slice and a horizontal washer. So capital R of y is going to be the distance from the axis of revolution to the outer curve. So this is x equals 2, and the outer curve here is x equals y squared. So right minus left, 2 minus y squared. Little r of y is the distance from the axis of revolution to the inner curve, and so that's x equals 2 to x equals y. So that's going to be 2 minus y. Again, right minus left, 2 minus y. So then our volume is going to look like this. And our y values, notice, are going from 0 to 1. So we're here, and that evaluates to 8 pi over 15. So just keep in mind when you're doing volumes by slicing, the disc or washer is always coming from a slice perpendicular to the axis of revolution. And with this, we'll complete our lesson on volumes by slicing.